Ever watched a single network cable choke under heavy traffic, or seen a link fail and take half your users offline with it? Welcome to Stage 2, Lesson 14, where we tackle that exact problem with EtherChannel and LACP, the technology that lets you bundle multiple physical links into one logical, faster, and more resilient connection. So here's the roadmap for the next few minutes. We'll start with the why. What bundling links actually buys you in terms of bandwidth and redundancy. Then we'll get into how EtherChannel works its magic with spanning tree, treating multiple cables as one logical port. After that, we'll compare LACP and PAGP so you know which protocol to reach for. And finally, we'll look at how traffic is actually load balanced across those bundled links. So let's start with the pain point that makes all of this matter. Picture two switches connected by a single 1 gig link with 48 hosts on each side. That's 96 devices fighting over the same pipe, which works out to roughly 10 megabits each when it's saturated. And it gets worse. If that one cable fails or the NIC dies, both sides go dark. Upgrading to 10 gig is pricey, and just adding more cables won't help either, because spanning tree will block every link except one. That's exactly the gap EtherChannel is built to fill. And here's the trick. EtherChannel lets you take anywhere from 2 to 8 physical links between the same two switches and bundle them into one logical link, a port channel. So those 4 1 gig cables between switch A and switch B stop being 4 separate paths fighting spanning tree and instead become a single 4 gig pipe called PO1. Spanning tree only sees that one logical port, so it has nothing to block. And if a single cable fails, the channel just keeps running on the remaining links. You get 4 times the bandwidth and seamless failover, all without touching STP. But before you go bundling ports together, EtherChannel has some strict rule, and if you break any of them, the bundle simply won't form. Every link in the channel must run at the same speed, the same duplex, and carry the exact same VLAN configuration, same access VLAN, or, for trunks, the same allowed list and native VLAN. Both ends also need to land on the same physical switch. Cross-switch bundling needs MLAG, VPC, or stack-wise, which we'll cover later. And the math is simple. Minimum 2 ports, maximum 8 active. Anything beyond 8 sits in standby, ready to take over if an active link drops. Once those rules are met, you have 3 ways to actually form the bundle. LACP is the IEE standard. It works across any vendor, negotiates the link, and crucially, shuts the bundle down if something's misconfigured. That's the one you should reach for every time. PAGP is Cisco's older proprietary version, functionally similar, but Cisco to Cisco only, so treat it as legacy. And static mode just forces the bundle on with 0 negotiation. Fast, but one mistake and you've built yourself a silent loop. Save that one for labs or emergencies. Now, once you've chosen LACP, there's a second decision to make. Should each side run in active or passive mode? Active means the switch actively sends out LACP packets trying to negotiate. Passive just sits and listens. So as long as at least one side is active, the bundle forms. But if both sides are passive, they'll stare at each other forever and nothing happens. The safe move? Set both sides to active. Negotiation completes instantly, and you avoid that silent passive-passive trap. Same logic applies to PAGP, where desirable is active and auto is passive. Now that the bundle is up, let's talk about how traffic actually flows across those links, because this part surprises a lot of people. The switch runs a hash on things like source IP, destination IP, and port numbers, and that hash decides which physical link the flow takes. The keyword here is flow. Every packet from the same source-destination conversation gets pinned to the same link. Why? Because if packets took different paths, they'd arrive out of order, and TCP absolutely hates that. The side effect, though, is real. 4 1 gig links don't give you 4 gigs for a single transfer. One flow maxes out at 1 gig. You get the full bandwidth only when you have many flows spreading across the bundle. And here's where you get to tune that hash. If you're working at pure layer 2, *c_dest_mac is your safe fallback. But for most modern L3 topologies, SRC dest IP is the recommended choice. And if you want even finer granularity and say lots of flows between the same two servers, go with SRC dest port, which pulls in the layer 4 port numbers. One critical tip: configure the same method on both ends of the link. Otherwise, traffic distribution gets skewed and you're back to debugging weird imbalance issues. Now let's put it all together on actual Cisco gear. You select your 4 interfaces with an interface range command, then drop them into channel group 1 with mode active. That's what tells the switch to negotiate using LACP. From there, you configure the illogical port channel interface once, and those trunk settings cascade down to every member port. Set your load balancing globally, and verify with Show EtherChannel Summary. When you see SU and every port marked with a P, you know all 4 are bundled and actively forwarding. Of course, in the real world, bundles don't always come up cleanly. So let's walk through the failures you'll actually hit. If both sides are set to passive, nobody starts the conversation. Flip at least one to active. Channel misconfig log messages almost always mean mismatched speed. Duplex or VLAN settings on the member ports, which is why you configure them as a range. If one link is carrying everything, your hash method doesn't match your traffic. Switch to SRC dest IP or SRC dest port. And if you ever see the port channel down while the physical links are up, check for a native VLAN mismatch on the trunk. The golden rule here: prefer LACP over static mode, because LACP catches these mistakes before they take traffic down. So let's lock in what you should carry forward from this lesson. EtherChannel takes 2 to 8 physical links and presents them to the rest of the network as one logical port channel, which is why STP stops blocking your redundant cables and lets every link carry traffic. Reach for LACP whenever you can. It's the open standard. And remember, at least one side has to be active or the bundle never forms. And keep this last one pinned in your head. Hashing pins each flows to a single link. So a bundle gives you more total capacity, not a single faster pipe. And here's your one-page reference to keep nearby. Think of it as the lesson distilled onto a sticky note. The pieces to remember: prefer LACP over PGP. Never use static mode outside emergencies. Make sure your bundled ports match on speed, duplex, and VLAN setup. And when you're picking a hash method, SRC dest IP is your safe default for most layer 3 designs. Screenshot this one. You'll come back to it when you're configuring bundles in the field. And that wraps up EtherChannel. Next up in Lesson 15, we shift gears from bandwidth and redundancy into security, specifically port security and DHCP snooping, your first real line of defense at the access layer. You'll learn how to stop rogue devices, block unauthorized DHCP servers, and lock down switch ports the way a serious network engineer should. Catch you in the next lesson over at Dargslan.com.